All right, recording is rolling. It is Monday, September 23rd. We're gonna go over some dynamics posters. You guys remember those thumbnail notes I handed out, or how about the posters hanging around the room? The same thing. We're gonna go through some of those, do some last week, do some today. I wanted to get to these textbook questions, but the pacing hasn't really worked out for today yet. But here, so I have three different sets because I have three different kind of classes. Here's for my AP students, here's for my conceptual students, here's for my honor students. And I don't have a due date on these yet, but I won't be picking these up until at least next week. Right, so definitely not this week because I want to solve a bunch of these with you guys in class so you guys can get some practice as we go along. Maybe give you guys some independent practice at some point. Also, I want to fit in a couple of labs this week if I can. It's going to be an action-packed week. So tomorrow, have you guys do a friction lab, which is going to be in two halves, part one, part two. And then Thursday, if I pace things out right, have you guys do an Atwood lab. It's going to involve these pulleys and some string, possibly. Right. So tomorrow, I will hand you guys this page. Here's friction lab on one side. We got here's the first half, here's the second half. Later today, I'll show you guys what the two halves are. They're going to be two different perspectives on friction. On the back side of the same paper, I printed the Atwood lab. We won't get to this for till a few more days, right? But hey, look, there's like a little pulley here and some string and some lab weights. Hey, right. So I'll show you guys later today kind of what those look like. So you can, okay, so one thing at a time. Right, then for context, first we had a reunification drill this morning. Right, so just for, oh yeah, that's right, that's that day. Right, so it's Monday. So you guys good so far? Good so far? All right, let's flip over to posters. Be kind of a good pace here. Here we go. Let's get, oops, all right. There's a Paul Hewitt, just not quite yet. I'm gonna save him for a little bit here. All right, here we go. All right, so back up a little bit. All right, so you guys remember we started with these silver banners, right? There's measurement, there's geometry, algebra. I've got some, you got a little trigonometry down here, sine, cosine. Right, then for a few weeks we were doing these red banners. Right, this is kinematic motion. We got drop a ball off a cliff, type linear motion, car starts, car breaks to a stop. Then we went over to projectiles. Right, we got cannons firing cannonballs. Took these launchers out to the balcony. All right, now we're moving on to the orange banners. Orange banners is what we got. This is dynamics. You see Newton's laws of motion. I see forces. I see lots of free body diagrams. All right, we got 2 pages of these. All right, time out. Let me pause this video, take this phone call, resume. All right, we're back recording. So you guys have 2 pages of these orange banner thumbnail notes. Same posters hanging around my room, so it's at least 32. And there might be a few that didn't quite make the cut that might show up here too. All right, so you guys good with context where we are in the class? Let's take a look here. Now, some of these I was going through yesterday, so I'll zip through these a little bit faster, but it's good to see it second time for a little bit of review. And then some of these are going to be new. I'll go through these a little bit slower. And at least one of these, we're going to switch over and actually do notes on a paper. Right, so you guys all got your notebooks out, or there's some paper on some stools if you need that. So you guys saw this one. We've got new variables and units. Right, mass could be in kilograms. Force, guys, a force is just a push or a pull. That's it. Force is a push or a pull. And there's various types of forces. They're all measured in newtons in this class, right? Now, tomorrow, you guys are going to be doing a friction lab. Do you guys see these right here? See this Greek letter mu in this class that usually stands for coefficient of friction? That's a ratio of 2 different forces. It's friction force to normal force. I'll pull up a free body diagram pretty soon and show you guys. I'll point it out exactly what that is, right? Guys, if you take a ratio of 2 different forces, like newtons divided by newtons, does that come out like unitless, basically? Right? This is one of the rare times in this class where there's ever a unitless value, but it's really newtons per newton. And then the bottom here is spring constant. How stiff is a spring, basically? You guys had some spring scales. They had different types of springs on them. Right? You can quantify that newtons per meter. Right? So 1 Newton, it's how we're going to quantify force. Right? It could be a tension force. It could be a weight. It could be different kinds of forces. Is it newtons? 1 Newton breaks down into 1 kilogram meter per second squared, which makes sense if you think about Newton's second law of motion. See if you guys remember this from last week. Guys, what was Newton's second law of motion? It's a real short formula. It goes what? F equals ma, right? You guys remember F equals ma? Force equals mass times acceleration. Well, let's look at these units and see how it all lines up. Force could be in newtons. Mass could be in kilograms. Acceleration could be in meters per second squared. You see how all pops in place right there, right? It all lines up exactly, right? Another unit you might see is, pressure could be measured in pascals. There's different ways to measure pressure. Pressure is force per unit area. So in this class, it'll be pascals, which is Newton per square meter, same thing. Right? If you ever say buy a bike pump, it says pounds per square inch. It's the same concept, just American units. Okay. Right. You guys saw that? You guys remember Newton's laws of motion, law of inertia, anything at rest state rest, anything in motion wants to maintain its velocity unless there's an external net force. I'm going to go change this poster. I'm going to put the word net in here. External net force is really what it is, right? Newton's second law of motion. You guys just told me F equals ma. Really, I like the fraction form of it. I think it shows cause effect a little bit better, right? Where do accelerations come from? Well, it comes from a net force acting on some mass. You think of that, right? Right. And guys, before I flip the screen, you guys tell me, what do you guys think is the next slide? Newton's third law. And how does that go? What does Newton's third law say? For every active force, there's a equal and opposite reactive force. Aha. Now, so Newton's third law, this is the equal and opposite rule. Remember, guys, for this one, you need two different interacting objects, object A and object B, that are somehow pushing or pulling on each other in some way. Okay? Could be a cannon and a cannonball, could be a planet and the moon. Okay? And the force interactions are always equal and opposite. Now, we did some free body diagrams last week. If you look at your notes, you probably see some free body diagrams. Is these free body diagrams, we tend to just focus on a single object at a time, like only object A. But don't forget, there's another half to each story with these forces. Right? Right. What else we got? Right. Another Newton's law. Right. This way I did show you guys also. Acceleration now is this bridge variable between kinematic motion and dynamics. You guys know acceleration is a rate change of velocity, and then I take the three kinematic formulas, rearrange them here, solve for A. Okay. Now you have a new perspective on acceleration, where it comes from. And this is Newton's second law of motion. Put it together. Suppose I ask you this question. You kick a soccer ball. Say you know the kicking force, you know the mass of the soccer ball. Let's say you know the time interval, your foot is in contact with the ball, and the ball starts at rest, for example. There's enough information there. Start with dynamics, bridge over kinematic motion, where you can solve for the speed that the ball leaves your foot. It's all right there, right? I think this is one of your thumbnails too, isn't it? So you guys got all this, Right, you guys remember Hooke's law? That's how the spring scales were operating. F equals kx. I want to do the lab version with you guys eventually, probably next week. I think I can fit in. We'll see. All right, free body diagrams is, guys, only what kind of vectors right now? What kind of vector? Is it force vector or velocity vectors? Force vectors, right? That's all I care about right now, force vectors. Right? In a few months, we might bring in like torques and moments, right? All I care about is force vectors. If I ask you a quiz question, say draw a free body diagram, are you guys going to draw velocity vectors? No. All right, here we go. I think some of these showed up in the free body diagram PowerPoint last week. Suppose there's a rocket in deep space at constant velocity, maybe something like that. Right? Let's break this down, guys. Constant velocity. Anytime you see that phrase, constant velocity, what do you know about acceleration? Zero acceleration. Hey, let's tie in with Newton's second law of motion. If there's zero acceleration, what do you know about the net force? Also zero, like 0 newtons. Right. And if you're in deep space, now let's go in deep space. Well, you just don't need any forces at all. Right? If you're in a moving vehicle, you're just going. You're just inertia. You're just coasting. You don't need any forces. Oh, yeah. Yeah. What does net force mean? As net it means suppose there's like multiple forces acting on something. You add all the forces together, like as if there's like some net effect, as if it's a single force, right? Like each of us right now is sitting at rest, right? But each of us right now has basically two forces on us, right? There's the weight gravitational force down, and if you're sitting on a chair, the chair's holding you up, and that's called a normal force. You guys remember normal force? And those two are exactly canceling out. So there's zero net force. If there's zero net force, you say, oh, none of us are accelerating. So we got, okay, there you go. So great question there. All right, what else we got? Ooh, how about air hockey puck moving across the constant velocity? I think you guys may have seen this one too. Now, when you strike the puck with the paddle, there would be a horizontal force. That would be true, right? But this snapshot, what you guys are looking at right now, that's all in the past. Right? So it's been hit in the past, maybe like a second ago. And now that puck is just coasting across the table at constant velocity. Now, it's moving horizontally. Does it need a horizontal force to keep moving horizontally? Nope. There's two vertical forces. They balance out. Right? So what else I got here? Right. Okay. Right, guys, we're getting closer to tomorrow's lab. Guys, tomorrow's lab, you guys see this right here? This is the first half of tomorrow's lab. Let's take a look at this. You got a block, you got a spring scale, you're pulling the block at, look at this right here. Guys, constant velocity. constant velocity. What do you know about the acceleration and therefore the net force? It's all equal to what? 0. Right, so you think all your forces have to balance out? All right, now it's time for Paul Hewitt. Guys, how much force is he pulling with? 3 newtons. 3 newtons. You guys see 3 newtons? Right, hold on to that. Right, now hang on a minute. If he's pulling with 3 newtons of force, but was he pulling at constant velocity? So what was the net force? 0. Had to be 0. Hold on, if he's pulling with 3 newtons of force, does there have to be another force on it to zero it out? What was that other force called? Friction. Friction. In fact, you guys know how much. Guys, 3 newtons, right? He's pulling with 3 newtons one way. Friction is resisting at 3 newtons the other way. That's why it's a wash. That gives you constant velocity, doesn't it? Right? You guys get that? Right. Now let's add a little bit more to the story. Guys, what is the weight of that block? 6 newtons. Right. So when he had it on his flat horizontal table, that surface was holding up with how much force? How many newtons? Also 6, right? It's got 6 newtons of weight. Should be 6 newtons normal force to hold it up, right? He goes on to talk a little bit more, but pretty much we just filled in all those blanks right there. Let's go back to this right here, right? Do you guys see we just filled in numerical values exactly for this slide for Paul Hewitt pulling a block across, right? Again, this is the first half of your lab tomorrow. Right? So the block weighs 6 newtons. Mg is, so it's mass times gravity field, 6 newtons. Here's what does F sub n stand for again? Normal force, right? And what does normal mean? If 2 lines are normal, they're perpendicular, right? So, do you guys see that this surface force is perpendicular to the surface itself? That's where the word normal comes from, right? So this was 6 newtons, this was 6 newtons to cancel out the verticals, the forces vertically, right? Now he was pulling with 3 newtons. He said, well, it's going constant velocity, therefore the friction must also be 3 newtons to cancel out the forces horizontally. Let's got that, right? Now let's take a look at this green box right here. This is Greek letter mu, subscript k. That stands for, in this class, coefficient of friction, coefficient of kinetic friction if they're sliding past each other. Okay, right? Coefficient of friction is the ratio of 2 of these forces, specifically friction force divided by normal force. Right? Now, if this was 3 newtons and this was 6 newtons, then what was the coefficient of friction between Paul Hewitt's block of wood and his lab table surface? What's 3 divided by 6? 1/2. Is that like 0.5? Is that 0.5? Is that right? Okay, you guys get that? Do you think you guys can do that tomorrow? Yeah, tomorrow. Same thing. One more little detail here. Let's look at the pink box real fast. We got the coefficient of static friction. Do you guys see how it's an inequality? Here's why it's an inequality. Because you think you can apply a tiny, tiny force and the block doesn't move, and then a slightly bigger force, and you keep increasing the force, and for a while it doesn't move at all. Okay, that's why it's an inequality, right? Another detail is that usually it takes more friction to break the initial, it takes more force to break the initial friction than it does to keep it going once it's going, right? So usually mu(s) is larger than mu(k), right? So you guys good with that so far? Right. I'm gonna have you guys focus on just the kinetic friction tomorrow. All right, next slide. Turns out this coefficient of friction is a material property. So once you know what materials you're working with, you can know what the answer is gonna be. Like for example, if you're pulling steel against steel, you're going to have like these numbers right here. Here's the kinetic coefficient of kinetic friction. Here's coefficient of static friction. Right. Let's look at the bottom 3 rows. You guys see tires in icy road, tires in wet asphalt, tires in dry asphalt. Right. Now these numbers might not be exact. They're kind of middle. When was the road paved? How bald are the tires? Right. Okay. So we're kind of cutting through that. But right. Guys, what is it most difficult to brake on? Icy road or a dry road? yeah, it's really hard to brake on an icy road, right? You're just like skidding forever. And then conversely, I guess it's easiest to brake the car to a stop on a dry road, right? Do you guys see that? Here, let's focus on these numbers right here. Do you guys see the coefficient of friction from icy to wet to dry is increasing, right? This is like the friction force is 5% of the normal force. Here it's 40%. Here it's 70%. The friction force is 70% of the normal force. If the normal force happens to equal the weight of the car, whatever the weight of the car is, take 70% of that. There's your braking force right there. Right, you guys see that here? Right. But then I told you guys, I think last week, did we talk about, well, here, I'll ask you guys. There's a system in your car that actually allows you to, it's a computer system, allows you to brake the car faster than if the tires are locked. What's that system called? ABS, anti-lock braking system, right? Because what that's doing is it's rotating the tires a little bit to prevent skidding so that you can take advantage of static rather than kinetic friction. Because look at these three numbers on the right, right? 0.1 compared to 0.05, 0.5 compared to 0.4, 0.9 compared to 0.7. Do you guys see over and over and over the coefficient of static friction is larger? Kinetic friction? Okay. All right, so there you go. There's anti-lock braking. Moves you from the green numbers to the red numbers. You can stop the car faster. All right, so we got, okay, so here's the first half of your lab tomorrow. Can you guys do that? Okay, drag it across, record some numbers. I have a graph set up with some axes. You guys can make a graph probably. All right, let's check this out. All right, now we're getting to the second half of your lab tomorrow. This one's a little bit more involved. All right, so it involves a block on an incline. And now it's time to switch over. Everybody's definitely got their notebooks out, right? Got notebooks out, right? So here we're going to slow this down a bit because this takes some time to digest. Go ahead, write in your notes. Here's the title: Block on incline in equilibrium. Block on incline in equilibrium. There you go, right there. Okay. Now, guys, equilibrium, what does that mean the net force is equal to? 0 newtons. Right. Oh, you guys know this means the sum of forces? Right. The sum of forces is also called the net force at that. Right. Oh, guys, and if the sum of the forces is 0 newtons, the net force is 0 newtons. What does that mean is the acceleration? 0 meters per second squared. There's Newton's second law of motion, one version of that, right? Which means one of two things. I'm going to say either, okay, it could be option A or option B here. Right? Could the block be at rest? Could that possibly satisfy this? Block at rest, right? Either at rest, we say comma, or because there's another possibility. Guys, if you're in equilibrium, so that which is net force is 0 and acceleration 0, that's all the same thing. Right? You can either be at rest or doing what? Constant velocity, exactly, or constant velocity, right? Are those two, here, like, guys, if you're sitting in a parked car, I think it feels like sitting in this room right now. If you're sitting in a car going constant velocity along the interstate, then it feels pretty much identical, right? Indistinguishable. Right, so we're going to do this for an incline because I wrote the word incline. Let's get an incline going. Go ahead, zip off an incline. And I'll eventually show you guys how this is going to connect to your lab tomorrow. So be ready for that. Okay. You guys are going to, okay, like tomorrow you might set a lab weight on a surface and tilt it at some angle. Go ahead and set a block right here because it said block. Right, you guys draw a block right there. Right. Let's draw a center of mass dot. We were making some free body diagrams last week. We were focused on a single object. We got a center of mass dot, and we're going to draw some force vectors from that point. Right, guys got it so far? All right, now guys, for an incline, here, I'll throw in a little angle theta. Okay, you guys see I threw in an angle theta there? Right, so many degrees from the horizontal. Right. There's a whole class of physics puzzles that opens up just from this one premise. There's so many ways you can go with this question. And you guys are going to see some textbook puzzles that start with this, block on an incline. Okay? And for consistently over and over and over, the most straightforward way to solve these is to think in terms of a rotated Cartesian system. So that's the thing we're going to do. You guys see here, you guys see my ruler is parallel to the surface. Okay? And I have I'm dashing off an axis that goes straight through the center mass of that block. Okay. You guys see an axis that's parallel to the surface, right? All right. Well, I need an XY axis system, so let's go perpendicular to that. All right, so here's a line that's perpendicular to the surface. Pretty close right there. Okay, let's dash off this axis. So now I have a new XY axis system. Notice that it's not oriented to the gravity field. The gravity field pulls straight down, right? This is oriented parallel and perpendicular to the surface. Ooh, right? So you guys got all that in your notes. You guys drew an incline, some angle theta from the horizontal. You guys drew a block with the center mass dot, and then dash off a couple of axes, parallel, perpendicular to the surface. Right, everybody up to that point? All right, looks like you guys are about right there. Right, now, if this was floating around in space, would there be any forces? No. All right. All right. So let's bring this down to a planet surface, right, down here on Earth. Right. And I bet there's going to be a few forces on this, but what do you think the one is going to kickstart everything else out? Yeah, gravity field. Let's draw the weight. Right. Guys, does gravity pull straight down? Yep, gravity pulls straight down. So let's get going straight down. Oh, it's about like that. About that. Okay. And I'll label that force. Guys, what's a good label for gravitational force? mg. All right. Yeah, that's usually my go-to, right? Mass times gravity field. If you do F sub g, that's okay too. Force due to gravity. I'm doing mg. So mass times gravity field. This block can be some mass m. We'll label that too. The block is mass m, like that. All right. But you know what? Guys, this weight vector is not really aligned with my rotated Cartesian system. Now it looks like some diagonal from that point of view, doesn't it? Okay. So we need to re-express this weight in terms of this rotated system. That's going to be components. You guys remember vector components? It's about to be trigonometry time with maybe some sine and some cosine going on. All right. So let's do this. All right, here we go. So this weight is doing two things from the point of view of this rotated system. It's partly pushing the block directly into the surface. And it's partly trying to drag the block along and make it fall down the incline. Okay? So let's do those components individually. Let's go back to the center mass dot, and I'm going to dash off these components. You guys notice I'm doing dash lines. The reason I'm doing dash is I don't want to double represent my force vectors, right? So it's partly going that way, okay? And then partly this weight is trying to, there's some component trying to drag it along the incline, right? Right, it goes like that. Oh, guys, okay, guys, here's a really important detail right here. Right. Do you guys see how my roller is parallel to the surface? You guys see parallel to the surface? Right. So many years I've been teaching this class, and students really, I mean, not everybody, a lot of students struggle with parallel lines. You guys see parallel lines? Okay. Guys, am I holding my roller like this, like what, or to the ground, like that? No. Okay. You guys see I'm holding parallel to that inclined surface right there. So pull it back parallel. Can you guys see parallel lines? And right here, now you can dash off your other component. So put little arrowheads on it, arrowhead, arrowhead, right? You guys see I've just re-expressed the weight in terms of two components. You're gonna think about it. Okay, right. So now these components are aligned with that rotated Cartesian system. I said to. Right. And if you did this correctly, do you guys see a right triangle? A right triangle? Because which angle is the right angle? Which one's 90 degrees? This one right here? Right there? Okay, go ahead. Throw a little right angle right there. Bam. For the two components come together. You guys got a right angle right there. Right? And, what about, I wonder what is this angle up here? Maybe I'll measure it. Hey, do you guys think this angle looks kind of like this angle? You guys think it might be? I wonder if it is. I'm going to see. I'm going to do some empirical science. I got a protractor. Let's see, what is this angle right here? Now, I just made some angle. I'm about to find out what it is. It looks like 26 degrees. Yours can be whatever. It doesn't really matter. But mine happens to be 26 degrees. I wonder, what is this angle up here? Let's see. It's, whoops, got to get that line. Oh, it's 26 degrees. It's also 26 degrees. Oh, look at that. Theta is theta. Now, what if yours is like 31 degrees? Do you think that's also 31 degrees? It's always a match. It's always a match. Okay. Right. So go ahead. That angle is that angle. Now that's this reference angle. All right, that's going to help us figure out exactly what these components are. I know this is all in terms of variables, but you can have numbers. This could be a 10 Newton weight. This could be 30 degrees. Right? You can come up with numerical values for these. Right? We're doing kind of abstract here. Right? Guys, what is this component right here equal to? What times what? Start with here. Start with the hypotenuse of a right triangle. Here's the hypotenuse, right? We're going to start with mg times, is it sine or cosine of this reference angle? Sine, yeah, sine. Mg sine theta, because it's opposite. Because we're translating from hypotenuse to opposite of the angle. Yeah, that's a sine relationship. Okay. Okay. Well, if that's mg sine theta, what do you think this leg right here is? Aha, mg cosine theta. Oh yeah, oh yeah. Right, you guys got that? Right, sine and cosine. It's coming back again. All right. Okay. Okay. Good so far. Okay. So from now on, I'm going to ignore the actual weight vector, and I'm going to think about it in terms of the components to solve whatever question might be asked. Okay. All right. Right. But that can't be the only force vector on it, because if it was, the block would be in free fall, which clearly it isn't. So, guys, do you think the surface of the incline is holding the block up, sort of? Right. And what's that force called again? The normal force. And normal means what? Perpendicular. All right. What is perpendicular to the surface? Should I draw a normal force? Oh, that's going straight up against gravity. Is that perpendicular to the surface? No. How about actual perpendicular to the surface? Hey, that would be aligned with this axis, wouldn't it? Right. Now, how long should the normal force be? Should be probably about that long, right there. That's about the normal force. Does that look about right, or do you think that's too short? Too short? How long should I make it? Exactly. Yeah, you guys see it? This mg cosine theta, I bet it's going to cancel out that. Yeah, so how long is mine? Mine's about 7.5 centimeters, so we do the same thing up here. 7.5 centimeters, boom, boom. Yep, there it is. I'm going to write that. So F sub n, that's the normal force. That's F sub n. Okay, and then parentheses will say, by the way, that equals exactly what you guys just said, mg cosine theta. Right? As long as there's nothing crazy going on with, like, if nobody's like pulling on a rope at some weird angle, then that'll pretty much always be true. Right? So the normal force is mg cosine theta. Right? You guys got that? Right. Now, suppose I stopped right there. Would that block at that moment be in equilibrium? See, I see that I see the normal force cancels out mg cosine theta. Right? So now the block's not accelerating this way. That's good. Right? Is there still a net force on that block? Mg sine theta. You guys see that? So is this block in equilibrium yet? Not yet. And here's where I want to do a little side thought with you guys. Do a side thought. I have a few posters that are related to this block on an incline. We're headed towards this. We're not quite finished yet, but I want to do a little pause break because at this point it does look like this one, which would be a zero friction incline that only has these two forces on it. That's all we've done so far. Of course, the way it expressed in terms of its components, right? And I wonder what you could solve out of this. Well, if the net force, you guys see the net force would be mg sine theta, because that and that cancel. So mg sine theta is all that's left on the board. Okay. Let's do Newton's second law of motion. For net force, I'll put in mg sine theta, because that's the net effect. It's acting on a block with some mass m. Mass goes away. Okay. Oh, okay. So if you either took an air hockey table and inclined it at some angle, and the air hockey puck and swipe down, right? No, there's no friction, of course, right? But it would accelerate exactly this way. You know where else you guys have seen this? Guys, did you guys do a Hot Wheels car lab? Hot Wheels car? Okay. You think it was pretty much like this? Okay. How many guys, I bet some of you guys were like taping lab weights onto the cars and seeing how does that affect the motion? And what'd you guys find if you tape lab weights onto the cars? Yeah, it didn't affect it at all. It's like, it's still going the same distance. I know it's accelerating, but it's the same. That's right there, isn't it? Now you guys found the empirical version, but here's the dynamics proof right here of why it's going to cancel out. Right? In fact, while we're at it, Oh, okay. So this is for all the cars, regardless of the mass. You guys know Earth gravity field at this point. Do you guys remember what was your angle of incline? What was your angle of incline for those cars? 5 degrees about? You guys remember about? Right, some of you guys got 4 degrees, some of you guys got 6 degrees. Let me throw in 5 degrees. Let's solve this right now. Let's see, what is Earth gravity? I'll round it to 10 meters per second squared times sine of 5 degrees. All right, and this should represent right here how much your cars were accelerating down the incline. So it's 0.87 meters per second squared. So basically less than 1 meter per second squared. So they were accelerating. All the graphs that we did a few weeks ago were showing that, but just kind of slowly. Right, I mean, compared to free fall of Earth. All right, guys good? All right, so that was a little side thought. We did a little side trip right there. Let's get back to this though. All right, so we still have to make this block equilibrium. So we still need one more thing, which is what? Friction. Friction. All right, so let's go back here. Now, see, if I don't have friction, then the net force would be this mg sine theta. We got to cancel that out. So which direction are you going to draw friction? If this is down to the left, friction's got to point up to the right to cancel that out. And how long should I make it? How long? Should it exactly cancel out the mg sine theta to zero out along this axis? I think it should. So I'm going to label this F sub FR, right? So friction force. And then parentheses will say, by the way, that needs to be equal to mg sine theta, so that the force zeroes out along that axis. Right, now all your forces cancel out. Now you have equilibrium. Okay. If the block is at rest, then this would be static friction, and you could have at rest that guy, okay? Right? Or guys, what about this? Could the block be sliding down at constant velocity? That would still be equilibrium. So this would switch over to kinetic friction, but otherwise the free body diagram would look exactly identical. That could be that too. All right, you guys good? Okay. And so this is the first time you do this. This will not be the last time you guys draw that diagram. Okay, so want to take some time to do that. So you guys good? All right, so switch back over to these slides. All right, so that's that guy right there. All right, you guys good? All right, block on incline, equilibrium, boom. That's exactly what's in your notes now. Right. I've got a few slides related to this. Let's look at the other ones. If you just focus on normal force as a function of that angle, do you guys see this horizontal surface that gives 0 degrees to the horizontal, then about 30 degrees, 45 degrees, 60 degrees, 90 degrees? You guys see that? Right. I put the same block over and over. You can tell because it's the same weight. Mg is the same. That green weight vector is the same over and over. Okay. Oh, but look at the surface force, this normal force holding it up. Going from left to right, it's getting what? Shorter and shorter. It's smaller and smaller. That's what this is what you just wrote in your notes, isn't it? You just read this a minute ago. Normal force is mg cosine theta. And what's cosine at 90 degrees? 0. Because if you take here, if I take this object right here, put it right up against the vertical wall, right, and then let it go. Right. When I let it go, the wall doesn't even push back against it. That's that last picture right there. Is that? All right. Plus we got 0 friction. We were just looking at that. That's your Hot Wheels car right there. Here's your Hot Wheels car. We just did the calculation. Right? Hot Wheels car. And it only has 2 forces on it. Weight down and then normal force up to the left. So there's a net force of mg sine theta. Did that one. Okay. All right. This one right here. Okay, guys. This is the second half of your lab tomorrow. This one's a little trickier. What I have you guys do is take some lab weights, put them on some surface that you can tilt. It could be your desk. It could be a physics textbook that you could like lift at some angle, right? Now, I really debated, like, should I show you guys the slide or not? Because if I don't, I'm kind of leaving it up to you, which could have some advantages. Right? But you know what? I'm just going to go ahead and show you guys this today because this one's a little bit involved. And then when you guys come into class tomorrow, I'd be like, okay, I know I've seen this. I know how to figure this out. It's still going to take some effort. Okay? But guys, take a real good look right here. A real good look. This one takes some thinking. Here we go. So guys, sliding at constant velocity. Oh, sliding constant velocity. Isn't that exactly the free body diagram that's already in your notes? We just made that. Same diagram, right? So I know this could be kinetic friction, but okay, we got that. Right. Constant velocity, does that mean 0 acceleration? Yep. That means 0 net force. That's the sum of the forces is 0. Yep. That's also true along each axis. Let's focus on this axis parallel to the surface. Right? You guys see this axis parallel to the surface? Right? So I see friction force pulling one way. I see mg sine theta pulling the other way. Set up this equation right here. has to zero out. That's true, right? Zeroes out. Okay. Then let's do some algebra. Slide this green term over. That's over there. Hey, you guys remember a few minutes ago, I said, how long should I make the friction force? And you guys said, oh, well, it's got to cancel out the mg sine theta. So it should be the same length. See that length? Is that length the same length? Okay. Hey, that's already halfway down, right? So already a few minutes ago, we already kind of worked like halfway down this page, this proof already, right? So this friction force is equivalent to mg sine theta. That length is equal to that length. It cancels out. Right, guys good? All right, next line. I did a little substitution here. You see friction force, I'm calling coefficient of friction times normal force. You see that? Let me show you guys where I got that from. I'm going to rewind a little bit. Guys ready to rewind? Bing. Right here. You guys see this right here? Right here. Coefficient of friction. I know it was the ratio of friction force to normal force. I remember that, right? Right. Can you guys cross multiply the normal force? Get friction force is equal to coefficient of friction times normal force, right? Mu times F normal. You guys see that? It's just this green box rearranged a little bit. It's okay. All right, let's fast forward. Go back to the future. Bing. All right, now we're back here. That's this right here. Okay. All right, guys good? All right, next one. Hey, this normal force. This normal force. Is that mg cosine theta? We've been talking about? We did that a few minutes ago. That's in your notes too. I just substitute that in these brackets right here. You guys see in brackets that substitution? All right. So it's a bunch of little steps that just follows the logic of what's already in your notes. Now this last step is where everything comes together and just clicks all at once. So is what cancels out on both sides? What cancels out? The m and the g. Yeah. So the weight. So the mass and the gravity field. Right? Now you can test this tomorrow, but I'm making the claim now. You guys debate whether I should spoil this or not. That if you have small lab weights and medium lab weights and large lab weights, that the mass should not factor into the answer, right? The mass itself should cancel out, right? And the gravity field for that matter. So if you do this experiment on Mars with a weaker gravity field, should you get the exact same results? Yeah, so I'm making that claim too, although it's kind of hard to test, but if you did, right? All right. What I'm telling you guys is that all you need to determine the coefficient of friction is a protractor. Isn't that how you could interpret this last line? So sine divided by cosine, that's where tangent comes from. Right. So making the claim that this is the case, yeah. Once you guys see it today, say, okay, that's interesting. And then tomorrow you guys come in and I'll see if you guys can do that from scratch. Okay. You guys think? All right. So we got next here. Okay. So there's the second half of your lab tomorrow, basically. So some version of this, have you guys do a graph, something like that. All right. The rest of these slides, I've got some review and some stuff that's new. It's a little bit of mix. All right, so this one's review. You guys have done this one. So I got a weight hanging down. I got a spring force up. For that matter, spring force is at F equals KX, Hooke's law. Okay, so we got that. Boom. Next. Chain gang. You guys did this one. You guys remember this one? Got a large tension at the top, medium tension in the middle, a small tension at the bottom, something like that. You turn this horizontal, make that a train. Choo choo. See that? We got, guys, elevator physics. There's a whole class of physics puzzles that's this right here. This right here. A lot of your textbook puzzles that we're going to do later this week. This is going to be a starting point. So suppose you're standing on a scale in an elevator. What if the elevator is accelerating upward? Do you feel really heavy? Yep. And the physics interpretation goes like this. The normal force, the scale pushing up on you, is more than the Earth is actually pulling down on you. Right? So there's an unbalanced force. Hence you'd be accelerating upward. Okay? And that could really be one of two different things. You might be moving up faster, faster, faster. But don't forget, guys, what's the other way to also accelerate upward? Moving down, doing what? Slowing to a stop, right? Moving down to slow to stop. And if you're out of context, you just feel heavy in an elevator, you don't know which one of those it is. You might be moving up faster, you might be moving down slower. You don't. Right? They feel identical. The scale rating is going to be right. All right, guys. Here's the full proof, and then at the bottom, I think we did this a little bit, maybe last week. Right. I can tell you the normal force reading on the scale is going to look like this for accelerating up. Okay. All right. Next slide is, well, what about other situations? So here's accelerating up on the right. Here's accelerating down on the left. And here's equilibrium in the middle, right? And then any of those three scenarios might have a bunch of individual stories attached to them. And I wrote all the stories around, right? You guys see, like, for example, equilibrium might be at rest, might be constant velocity. And if it is constant velocity, it might be moving upward or downward, but it doesn't even matter. And here's some equations at the bottom, right? But they all kind of come from, if I go back a slide, to basically this proof, just rearranged a little bit. All right. So, right. Oh, now if I pace things out right, I want to have you guys do this lab on Thursday if I can. Can you guys take those red pulleys, take some string, attach some lab masses, and see how does it accelerate? Do you guys think? Okay. Now acceleration, the old way to think of it, which is what you're guys going to do, is say, well, how far does it fall and how much time if it starts from rest? Can you guys calculate acceleration that way, right? And then how's that going to connect to the masses, the individual masses, M1 and M2, right? So guys, this one's kind of involved, takes a lot of thinking. There are methodical ways to solve this, and I've got some setups over here. You guys see these 4 boxes. Do you guys see the first box is Newton's second law of motion? You see that? All right. Now, how you continue from there depends on which textbook you pick up or what teacher you have. So I just put the idea out to start with, and we'll solve some of these in the next week or two. I like to solve these from a systems point of view, which is like look at the whole system. That's like kicking off to this yellow box right here. A lot of textbooks, a lot of teachers will actually start with a system of equations. They'll say, let's focus on M1 and M2 individually, which are these 2 green boxes. They'll make a system of equations. You can really solve for 2 things. You can solve for the acceleration. Furthermore, you can also solve for the tension in the string that connects them together. Okay, so there you go, big picture that's coming down the pike. We're going to solve some of those, right? And you guys are going to do a lab. Right? Oh, there's also here the second half of this lab is a modified version. Hey, what if you like put a Hot Wheels car up here or a low friction surface, right? So that there's one weight that's driving everything. That's this M1G over here, right? But this M2 up here, I think it's providing inertia. It's probably slowing things down because of inertia. But its weight is actually being canceled out by the surface normal force. So, all right, I wonder how that's going to play out. It plays out a little bit different type motion, right? Again, give you guys a lab, see if you guys can figure that out through a lab, right? And then we'll solve this methodically using, say, these boxes I got on this poster anyway. What else we got? Okay, lab tables. All right, let's do, all right, I think you guys saw this last week, maybe. If you have a joint in tension, these diagonals I can break into components. The right pulls right as much as the left pulls left. The 2 upper components pull up as much as the weight pulls down, zeroes out. What if the angles are different? What if you have like asymmetrical? It's still the same guiding principle. So now you have sines and cosines and alphas and betas, a little bit more complicated, but the same guiding principle. This one pulls right as much as this one pulls left. These 2 are pulling up collectively as much as the weight's pulling down. And then you might have to do a bunch of algebra. It might be a bunch of substitution. But you can solve for things like, well, what is the tension in the right string? Right. All right. This I want to do with you guys one day. That one's fun. Right. Oh, there's you guys solved this the other day. Remember, I asked you guys, said, how does that Pythagoras cup work? Right. So we walked through the solution a little bit more. If you look at Friday's video, we walk through the solution. So that one's posted on the last video. Right. Right. Car brakes to a stop. I know we just got a couple minutes left here. This car brakes to stop, I think it's in your notes from last week too. I think we did this for by a diagram. Now, interestingly, do you guys notice what variable cancels out by the time you get to the end of this proof? Guess what variable canceled by the end? The mass of the car, right? So if you have an empty car, let's say you go to the grocery store and stock up like it's the next COVID on the way, right? And you walk back home or you drive back home with like a bunch of groceries. Right? Let's say you break both those cars. Are both going to break at the same rate? Yep, mass canceled out. And there's an extension question, which how much road does it take to come to a stop? This question is going to come back. You guys are going to see this question over multiple sections in this class. There's some version of that. Okay. There's a plane. Guys, I know this is a military interest question. I asked students earlier said, oh yeah, this is totally showing up on the ASVAB. Do you guys think thrust force and drag force cancel? You guys think lift force and weight cancel? So guys, you go in the military, they might ask you, what's the forces keeping a plane at constant velocity? And they're looking for this right here. You just name those 4 forces: up, down, right, left. Also got, I have some related to drag. Do you guys think, go to the edge of a cliff and drop a ball, you got free fall. Now, if you introduce air drag, do you think the faster it's falling, the more the air drag picks up? And that process continues until you get to this picture on the right. Guys, what's the net force on the picture on the right? 0. So that's equilibrium. Does it fall down at constant velocity? What's that constant velocity called? It starts with a T. Terminal velocity. Right. Now it turns out that drag force picks up with speed because drag force is proportional to speed squared. Here's the full equation, right, which we might not apply it here, but I do remember seeing this equation pop up a few times in college. So if you go like a math, science, engineering route, I see that. Right. All right. Coefficients of drag, other parts of this. This would be a good one to have you guys do. You guys see velocity versus time. If there was no air drag, it would be a straight line with the slope of gravity field. But if there is air drag, it's going to eventually asymptotically approach this terminal velocity, right? So like that. All right. Yep, that's where I wanted to get you guys today. All right. So tomorrow the plan is friction lab. Wednesday my plan is to solve textbook puzzles with you guys, and then everything paces out right. I'd like to fit in the Atwood lab day after that.